Great. Okay, nice to have everybody back. Uh, Two quick things before we jump straight back into content. So first, to be very clear, because of kind of jumping through the material and things, I want to stress that you don't have to know any of this stuff from the slides on pure sets or on ordered pairs. I'm going to leave them in the slides because I think it's interesting, it's worth knowing about. But I won't ask you any questions or anything like that about them because we didn't go over them in here, okay? Just to make that very clear. That was the material we kind of skipped when I said like, oh, I just want to show you this stuff, but I'm not going to talk about it. So I won't ask any questions about it. Yeah. Functions are important. Yeah. Okay. So, and also relatedly, because of time constraints, I won't bother talking through the infinite set stuff. I'll upload an old recording of it. It's just for funsies anyway. It wasn't going to be anything I was going to examine you on. It's more kind of, hey, this is just really cool stuff, like rather than actually like, oh, this is stuff that I think it's stuff that everybody should know about, but also not stuff that I was going to necessarily like examine you on. So it's no loss that we don't cover it. What I'd like to do though is take the rest of our time, quickly talk through Russell's paradox. I don't think that will take us more than 5 or 10 minutes. And then finish up by talking about some properties of relations. So I should say before we do both of these, right, the Russell's paradox stuff is again, this is information I think that everyone should know. I'm not going to ask you any questions about the section on Russell, right? It's not going to be on the final exam or anything like that. But I think this is just worth knowing. When it comes to the properties of relations, I'll flag up the stuff that's going to be immediately pragmatically important for you to know, but I'm also going to give you a lot more stuff too, because I think, again, it's helpful for you to know some of this stuff. Right? Not just for this, but more generally. Okay, so Russell. So I already introduced to you the axiom of extensionality, which is that, right, two sets are identical if and only if they have all and only the same members. Now, naive set theory, the kind of initial development of set theory, as we for our purposes, right, had the axiom of extensionality and the axiom of comprehension as its core. So extensionality tells you what are the identity conditions of sets, but that doesn't tell you how many sets there are. Right? When could you build a collection? Well, this doesn't answer that. It just tells you when are two sets identical or distinct. So we need another principle to tell us, cool, how many sets can we build? And an initial, naive idea is that as many as you want. Right? Think of any property, any condition. Right? Well, there's going to be a set of the things that satisfy that condition. Or put another way, think of any predicate that you can construct at all. Right? Any predicate in, let's say, English, whatever you want it to be. Well, there's got to be a set corresponding to the things that satisfy that predicate. That's what the axiom of comprehension says. For each condition C, there's some set of all of the things that satisfy that condition. So axiom of comprehension and extensionality together give us naive set theory. Naive set theory very quickly runs into a paradox, which again, I suspect many of you have heard of, but maybe not in its normal terms. So here's the paradox via analogy. Also, I want to say massive props to the barber here. This is sick. So here's the analogy. Take a small town. The small town is so small it only has one barber. And that barber follows a very strict rule. Right? The barber shaves all and only those people who do not shave themselves. He shaves all and only those people who do not shave themselves. So cool, that makes sense until you ask, who shaves the barber? Well, if he shaves himself, then he must not shave himself. Alternatively, if he doesn't shave himself, then following his rule, he must. Which of course means that he doesn't, which means that he does, which means that he doesn't, which means that he does, which you see the problem. Right? The only solution is the barber is the only man who's got a massive beard, right? Half bearded, half shaved. There we go. That's the best we can do. So again, this is the analogy. The analogy case sets up the actual set theoretic case. But if we get the analogy, you get the basic problem. Right? So on the naive set theoretic conception, given that sets can be themselves members of sets, there's nothing to stop sets from being members of themselves. Right? So for example, if we have set M be the set of all sets with more than one member, it looks like M should be a member of itself. Right? Similarly, if N is the set of all things that are non-buses, then it looks like N should be a member of itself. It's a set. Sets aren't buses. Buses aren't sets. Cool. Done. So let's have R be defined as the set of all things that are not members of themselves. Right? So R is the set of all things that are not members of themselves. Well, cool. All of us are members of that set because we're all individuals and individuals don't have any members. And lots of sets will be members of R. M and N, as we've defined them, won't be, given what I've got above, right? But these ones presumably all will be, right? They're in there. But what about R itself? Yeah. Please.
Is Russell a part of that set of people that negotiate themselves?
Yeah. So I mean, this is basically the analogy here is that there can't be such a set. Effectively. So we'll go through the set because it'll bring it out more explicitly. Right. So again, R, the set of all things that are not members of themselves. So we have a bunch of sets that are members of R. Is R a member of itself? Well, if it is, then it can't be. Because remember, the condition that R is defined by is not being self-membered. So if R is a member of itself, then it is not. And of course, if it's not a member of itself, well, then it must be a member, because it's the collection of all things that aren't self-members. So no matter which option you go with, you get the opposite result. So here's the problem. This set can't exist. If it exists, then we have a true contradiction. Right? And true contradictions are very bad because everything follows from a contradiction. Right? Remember earlier when we were talking about Mars's moons? If you have premises that are jointly inconsistent, anything can follow. Well, if we have a true contradiction, you can derive anything you want in your set theoretic system. No wonder you got that result. You believe in this nonsense. So Russell's paradox indicates that something is rotten in the very heart of naive set theory. And this broke poor Frege's heart, right? I mean, he was also a terrible, terrible anti-Semite, so fuck Frege. But still, you know, he was a really good logician. So something's wrong with naive set theory. And again, remember that really all naive set theory is defined in terms of is these two axioms. So something's got to give with one of these two. We've got to find a way to make sense of a set theoretic story, this basic idea that we talked through, which really all we had is these definition of membership and a definition of subsethood. So in response to Russell's paradox, set theorists have done a bunch of different things. One option is to distinguish between classes and sets. So we'll say that the axiom of comprehension applies to classes, but sets are somehow more restrictive. This doesn't really help though, because we can still get a Russell class. So that just moves the bubble in the carpet. Another option is you restrict membership such that sets can't be members of themselves, but this seems kind of overly restrictive. Again, if we think about, for example, N, the set of things that aren't buses, that looks like it should be a member of itself. Another alternative, and this is a kind of preferred option, is to adopt what's called an iterative hierarchical approach. So this is one where what you do is you start with members, you build the sets you can just from them, and then whatever you build next can only have stuff below. So you effectively build in something like this, but you explain it via the kind of construction methodology. This helps, but you can also generate some weird paradoxes for the iterative hierarchy approach. It also lends itself to a kind of constructivist approach to maths that many people find. And another option, and one that we'll talk about in the very last lecture, is just adopt a non-classical logic. That is, accept that there can be true contradictions and that this doesn't lead to explosion. We'll talk more about this again later. Yeah.
If a set is a member of itself, then wouldn't that lead to something like infinity mirror?
Yeah, so you do get something kind of weird, right? But the thing to remember is that membership isn't really a kind of physical relation, right? It's just a strictly defined relation. So I could just say that, right, being a member of is being the same height as is less than, right? Doesn't really matter. This is something akin to a broadly constructivist approach to set theory. Right? So you could get away with this in some ways. Right? It doesn't necessarily lead to actual infinities any more than this sentence is true does. Okay. So again, the fun part here is this beautiful, beautiful problem. Right? And it's so simple, yet so bad. And a lot of set theory has been trying to fix this, trying to get around this. And again, this is just something I think everybody should know. I think this is worth knowing. That's why I wanted to talk to you about it. Okay. So that's Russell's paradox, and it really poisons the naive set theory. Right? So from Russell onwards, people have tried to do various ways to get around this. But the core of your set theoretic approaches remains the same. The membership relation, subset hood, superset hood, which is just the inverse, right? The various functions. That's the stuff that's important for our purposes. So the last little bit that I want to talk to you about here are properties of relations. Now, I'm going to throw a lot of information at you here. I'm going to throw a bunch of definitions at you, but I promise that I will highlight the important ones. Now, this is stuff that, again, you've probably come across some of this terminology before, and I want to clarify it so that, well, also if you come across it in the future, you'll know exactly what some of these things mean. So when we think about relations, right, and we talked about two-place or three-place relations, when we think about the predicate that expresses a relation, we talk about the arity of the predicate. It can be a binary, a tertiary, a quaternary, an n-ary predicate. Right? That just means how many gaps does it have? So we can talk about an n-ary predicate if we want to be generalizing. Whenever we're talking about a relation, though, a specific one, we can also talk about the relation's converse. Right? And the converse is literally the opposite of a given relation. I know we define this kind of strictly. So we can say that is taller than, the converse of that is shorter than. Now note, what this really means is that for any two things, x and y, if x r's y, then y stands in the converse relation to x. So note, there's a bunch of things that aren't going to stand in either one of these. If you're the same height as, then you don't really get involved in this relationship. So is loved or loves, we can think of those as converse relations. Is loved by or loves, right? Again, it's just thinking about a relation in two different directions. Now, of course, for some relations, thinking about it in two different directions is just to think about the exact same relation. But that's not true for all of them. And in fact, one of the ways that I want to talk to you, one of the properties I want to talk to you about is exactly capturing that idea. So, the first property of relations I want to introduce to you is the notion of a reflexive relation. So we'll say that a relation is reflexive if and only if everything stands in it to itself. So is the same height as, if you allow for zero heights, is a reflexive relation. Everything is the same height as itself. Note, this doesn't mean you can't stand in the relation to other things, but a relation is reflexive if and only if everything in your domain stands in the relation to itself. Everything has a loop. Reflexive relations are useful. They're important. We use them in lots of different cases. We can also talk about variants thereof. We can talk about a relation being irreflexive. This is where everything does not stand in the relation to itself. Right? So is older than. Nothing stands in the is older than relation to itself. Yeah.
So reflexive is in the diagram when you put the arrow back on itself.
Reflexive means every node has a loop. Every node has a loop. If there's even one node that doesn't have a loop, then the relation is not reflexive. Irreflexive means there are no loops. And then you can sometimes see areflexive or non-reflexive. Right? This is where it's not the case that all of them do it, and it's not the case that all of them don't. That is, there might be a few loops, but not every node loops, and not every node doesn't loop.
Could we rewrite this as there are some that loop, but not all that loop?
Yes, that's basically what this says. Yeah. So yeah, again, reflexive means everybody loops, everybody R's themselves. Irreflexive, everyone definitely does not. And then a or non means some do, some don't. Example here, unfortunately, hates and loves. Right? Some people hate themselves, most people don't. Some people love themselves, unfortunately, some people don't. Know you were loved. There you go. But again, the important thing up here, reflexive. Reflexive is the important idea. Everything, so a relation's reflexive if and only if everything stands in relation to itself. Now the next property to talk about is symmetry. We can say that a relation is symmetric if and only if whenever x r's y, y also r's x. That is, if there's an arrow going one way, there has to be an arrow going back the exact same way. So is a sibling of is a symmetric relation. If A is a sibling of B, well then by God, B has to be a sibling of A. That's just how this relation works. Symmetric means it's a two-way street. So importantly, when we were talking earlier about converses, right? If a relation is symmetric, then it is its own converse. You just read it the other way, right? But non-symmetric or asymmetric relations will have to have a different relation as its converse. So, to go through some other terminology, right? So symmetry, again, means if it goes one way, it also goes the other. Asymmetric means it's definitely not that. It's not the case that. And this could be for lots of reasons. But all that matters is, again, that we have this, right? It's not the case that it's symmetric. And notably, we can also define up a notion of antisymmetric. We can say the relation R is antisymmetric if and only if, for two things, if x r's y and y r's x, then they must be identical. So the idea for an antisymmetric relation is that you never get arrows going back and forth between two distinct objects. one arguable property here is a part of. And that's because in mereology, kind of the logical approach to parthood, everything is a part of itself. It's the fullest part of itself, the biggest part. Right? But you never have two distinct things that are both parts of themselves. Arguably and interestingly, as we've defined it between symmetrical and anti-symmetrical, some relations are going to be neither. Right? At least as old as is neither symmetric nor anti-symmetric. Again, the thing for our purposes that I really want to emphasize is know what it means for a relation to be symmetric. Right? That it goes backwards and forwards. Right? Okay, so we've got reflexive, we've got symmetric. Yes?
I don't understand what anti-symmetric exactly means.
Good. So the idea here is basically that if you have a relation between two things, right? If it goes from A to B and from B to A, then it must be that they're actually the same. We want to make sure if the relation is anti-symmetric, that there are never arrows going back and forth between distinct objects. So that's the idea. It's supposed to say, okay, we can allow for reflexivity, but reflexivity is the only kind of symmetry that we will allow.
There are no arrows going from one node to another.
And back,
And back.
right? So here's the idea. You have node A and you have node B, and if the relation's anti-symmetric, you can have a node like this, or you can have an arrow like this, but you could not have that. Because if you had the arrows going backwards and forwards, what I was actually drawing was this. One node just arrowing itself.
This anti-symmetric allows the arrow to go from B to A.
It would allow for just one direction,
Okay.
but importantly, right, symmetry is always just about the goes from one and then it has to go back. If it's anti-symmetric, it will not allow for the return trip.
How is that different from asymmetric?
Good. So asymmetric requires that there can be no loops. In the fullest sense. Or at least, so versions of asymmetric requires that there can be no loops. Right? That's maybe the better way to put it. Right? Strictly speaking, as asymmetry is written here, it doesn't force you to have no loops. But there's versions of it that are even stronger that say, hey, you can't even have this. You can have no instances of symmetry. Okay. So again, reflexivity, symmetry. The last property that I want to mention is transitivity. I suspect that you've come across this notion in other cases. Right? Transitivity, a property, a relation is transitive if and only if you have three nodes, right? Whenever x r z, x r is y, y r z, then x r z. This is easier visually. If A arrows B and B arrows C, and if arrowing is transitive, then there's an arrow that goes from A to C. Is taller than is a transitive relation. If I'm taller than Amanda and Amanda's taller than Mira, then I'm taller than Mira. And actually, lots of relations are transitive, but many of them aren't. But generally, the idea of a transitive relation is you kind of pass it along. Again, formally, we can say the expression we have up here, right? For all x, for all y, for all z, if rxy and ryz, then rxz. Note importantly, what it means is that there's this arrow. It doesn't mean that you could get there using other ones. It means that there is this relation. This relation is there.
Why doesn't it mean that you can get there using the other one?
Good. So importantly, it kind of hinges on the idea that you can get there with the other ones. But it means, hey, if there are these, there's also this direct root. That's just what it says. In fact, that's sort of the antecedent is there's already this other way. We have the direct root too. So again, much like the others, we can talk about ways to kind of vary off of being transitive. So we can talk about intransitivity. That's just where it's not the case. Right? And this can be for lots of different reasons. My favorite example of an intransitive relation is eats. Right? If A eats B and B has eaten C, that doesn't mean that A ate C, right? Presumably because C has already been digested by B. Right? Again, eats isn't transitive. Right? Membership isn't transitive. Right? A can be a member of a set, and that set can be a member of a different set, but you don't have transitivity of membership. Yes?
So could we think of this as for all x, y, z, and then not for all x, y, z, and then for all not?
Yes, that is exactly the difference here, basically. So one thing that's annoying in all of these things, when it's about intransitivity or antitransitivity or areflexivity or irreflexivity, is people use terminology in lots of different ways. What I really want to drive home is the three basic notions: reflexivity, symmetry, transitivity, and then to highlight some of the basic ways to go, right? It's not the case that it is transitive, cool, let's figure out why, or it's definitely the case that it is not, right? So yeah, our last one's a very interesting one. Antitransitivity is when, hey, if the relation holds between the first two nodes, then it does not between the first and the third. So it's like, hey, if there's this relation, then there is not going to be this arrow. And my favorite example of this is beats in rock, paper, scissors, right? Because if it did hold, then rock would beat rock, and that would be bad. So, yeah. So again, reflexivity, everything stands in it to itself. Symmetry, if it goes one way, it goes the other. And transitivity, right, is if A goes to B and B goes to C, then A goes to C. You can pass it along. These three properties are big. They come up a lot. We'll often, at least in philosophy, also in mathematics, just simply stipulate that we have some arbitrary relation that satisfies these properties. This is why it's useful to know. So we can also talk about relations that have multiple versions of these. The one that I really want to mention is an equivalence relation. An equivalence relation is one that's reflexive, symmetric, and transitive. Right? So everything stands in it to itself. If A stands in it to B, then B stands in it to A, and you have the daisy chain. Equivalence relations are called because, well, is equal to is a version of one of these. Identity, indiscernibility, possibly. Weighs the same as, is the same height as, is the same age as, da 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 da. These are all equivalence relations. We can also talk about Euclidean relations. I'm going to skip over those because we've covered enough stuff, I think. Right? But again, the three that I really want to emphasize: reflexivity, symmetry, transitivity. Know those three. Those are useful to know. One thing we can also do once we have these notions is we can turn non-property relations into versions of them by talking about their closure. So if we have a non-reflexive relation, we can talk about the reflexive closure of that relation. And that is basically by adding whatever we need to make it such that it would work that way. So for example, if we've got our relation extensionally, and it starts off with Alf stands in it to Bart, Bart stands in it to Charlie, and Alf stands in it to Charlie, the reflexive closure of that is that, cool, let's add in all the reflective pairs. Right? The symmetric closing would be, let's say if it goes from A to B, then add in the pair that gives you B to A. Right? Again, these sorts of blank closures, useful when you're thinking about this stuff mathematically. This is why it's so useful to know these properties. So again, the general idea, reflexive, symmetric, transitive, you can then apply them to non-versions of the relations and generate the closed versions of them by adding in the appropriate ordered pairs or ordered in tuples. Okay. The very last thing I want to talk about, and again, I know I've thrown a lot of stuff at you, is a notion of a partial order. So a partial order, a relation R is a partial order, or a partial ordering relation, if and only if R is reflexive, antisymmetric, and transitive. So again, what does this mean? This means that, hey, everything stands on it to itself. For any two things, if they both are each other, then they must be identical. But you can daisy chain. Now, partial orderings are very helpful because the idea here is that you can start with some basic fundamental objects, and if it's partial ordered, then it's going to build up from there. That is, you have a foundation that's all kind of intermingled in a mess, and then the partial ordering is going to be everything that builds upwards. This is philosophically extremely useful if you want to talk about, say, hey, there's electrons, quarks, and leptons, and then everything's built from there. Cool, we've just got a way to formalize that. Or, hey, there's the null set at the base, and everything is built therefrom. Cool, then membership and set construction is a partial order. And it's only a partial order because it only gives you the ordering in one direction. A full order goes both ways. Again, I suspect that you'll come across this notion down the line, this notion of relation being a partial ordering. I want you to know what that means. Okay. Nice. So as I said, we're not going to talk through the infinite set stuff. Apologies, we're just time-wise, I don't think there's enough. But I want to emphasize some things today, right? So the main point of this lecture was to introduce to you some of these concepts. I'm going to set up, there'll be a set theory / relation little worksheet I'm going to upload this afternoon. Importantly, for practical purposes, the things I will ask you from this lecture, I'll ask you some definitions. Things like, what's the axiom of extensionality, right? I'll do some basic set theory operations. Give me the union of these two sets. Give me their difference, etc. And I'll ask you some basic definitions about reflexivity, symmetry, transitivity. Okay? Don't freak out about if it doesn't make a hell of a lot of sense. Again, this was just to kind of give you a taster. Now, next week starts the real work. Next week, what we're going to do is we're going to jump in to natural deduction. So I'll start by talking about what exactly natural deduction is and the motivation for doing it. And then we're going to spend the rest of the lecture just going through the rules for the deductive system. Okay? I would very strongly suggest that you read the chapter. Right? Again, I'll put the worksheet up on Canvas this afternoon. We'll talk more about the exam inspections and everything this week. Take care, and I'll see you guys all soon.